So thank you for the kind introduction and good afternoon, everyone. The work I will present in the next minutes was a collaboration of the Institute for Microsensors and Actuators and Systems and the Institute for Brain Research at the University of Bremen. So the main motivation of our work is to develop cortical visual neuroprosthesis for blind people to be able to restore some visual perceptions by electrical stimulation directly of the brain. And by the electrical stimulation, we can induce the so-called phosphenes. In literature, there's a lot of publications where intracortical microelectrodes are used to stimulate the cortex to produce the phosphenes. However, there's a main challenge using intracortical microelectrodes, the chronic stability. So to overcome this problem and also to reduce the invasiveness of the surgery, we decided in our approach to use an ECoG array and to place the ECoG array on top of the dura, which is the outer membrane of the cortex. And also we are using PEDOT-PSS as an electrode coating to reduce the impedance of the electrodes. And we also need this coating to be able to do electrical stimulation in a safe way. So I would like to show you the design of our ECoG array. The design was made for interfacing the visual cortical areas of V1 and V4 of the macaque monkey. In total, we have now 202 electrodes, each of a diameter of 560 micrometer, and also an integrated additional reference electrode, which will be flipped to the backside to achieve a skull-facing reference. The inter-electrode distance of the electrodes is 1.8 millimeter, and as a flexible substrate, we use polyamide, which is mechanically stable and also proved to be stable in saline condition. So here in the figure, you see the array head with the electrodes. We have also introduced some cuts into the array to increase the flexibility to be able to cover the brain curvature. The array head is connected via 3 separated flexible ribbon cables, and they end at a rigid part where omnetics connectors are soldered to interface the electronics. So I'd like to show you briefly the microfabrication of these arrays. We use silicon-based microtechnology. We start with an oxidized silicon wafer. In the first step, we deposit the structure and structure a gold layer, which will be used as a sacrificial layer to release the array after the fabrication. The first polyamide layer is spin-coated and structured. After that, we deposit the second gold layer to produce the conducting paths and the electrodes, and also for the soldering pads. And after that, we spin coat and structure the second polyamide layer to achieve the centered structure of 5 micrometer polyamide, 500 nanometer gold, and 5 micrometer polyamide. So in total, we have a thickness of about 10 micrometer. And to be able to release the array from the wafer in a safe way, we developed a lift-off process using a deep reactive ion etching of silicon and the sacrificial etching of the sacrificial gold layer using iodine solution. Of course, for that step, we have to protect the gold and the electrodes and the soldering pads. After releasing the array from the wafer, we solder the omnetics connector and we coat PEDOT-PSS using an electropolymerization process. So now I would like to show you the results of the microfabrication. This is the top view of the array with the electrodes, the connector parts. So we have 7 lattice connectors. And you see here the reference electrode, which is flipped to the back side and fixed with a biocompatible glue to have a skull-facing reference. Yeah. So after fabrication, of course, we did some in vitro test experiments to prove the stability. The impedance was measured at 1 kilohertz, which is approximately 700 ohm, mainly due to the serial resistance of the conducting paths and the spreading resistance of the electrodes. The charge injection capacity of the PEDOT coating was measured to approximately 2 millicoulomb per square centimeter, which is a value comparable to reported values in the literature. We also evaluated the long-term stability of the array in Ringer solution for electrical stimulation. So for visual cortical prosthesis, at the end we have to do many current pulses over a long time. And the question was, is this PEDOT PSS coating stable for this long-term stimulation? And we showed that also after a continuous current stimulation of 7 weeks at a frequency of 1 kilohertz, we couldn't observe any degradation of the coating, which gives us the result that the coating seems to be stable for electrical stimulation. We also proved that the electrode is stable for the steam sterilization process. Of course, for chronic implantation, we have to sterilize the array before implantation, and we couldn't observe any degradation due to the steam sterilization process at 121 degrees Celsius. So we implanted 2 arrays in 2 macaque monkeys chronically. We measured in vivo impedance at 1 kilohertz. The impedance, the range was between 2 and 20 kilo ohm, which is quite higher than compared to in vitro. And so the monkeys were trained to perform a fixation task. So they had to fixate a cross on the screen, and during the fixation, a bar was moving over the screen, and the recording, the activity in the cortex was recorded simultaneously. And with this experiment, we are able then to map the visual field of the eye to the visual to position of the activity on the visual cortex. And this is shown here in the 2 figures. So we have the results here you see are for 2 different electrodes recorded 3 months after implantation. And you see here the X and Y eccentricity of the visual field, and the color bar gives the normalized LFP power during the recording. And so the results shows that we are able to distinguish between different electrodes. Yeah. And with that, I would like also to conclude that we designed an optimized array for placement of for the visual cortex to cover V1 and V4 simultaneously. Our PEDOT PSS coating enables us a low impedance and gives us the capability for microstimulation. We also showed you that the presented ECoG array is stable for chronic recording of the activity, and of course the next step we are now going to do the first microstimulation experiments to evaluate the capability to produce phosphines directly in the brain. And with that, I would like to thank you for your attention.